Okay, welcome to our lesson on the derivative of polynomials. So in previous lesson we came up with our power rule. The derivative of x to the n is equal to nx to the n minus 1. So that simplified our derivative calculating process greatly for a large group of functions. But now we're going to extend that group of functions that we will have rules for to all polynomials. So we're going to start with a rule that we call the constant rule. This is a pretty simple rule. So if you have a function f of x equals some constant, so just some real number, so think of, it could be f of x equals 2, 3, 4, or whatever. F of x is a number. So what's the derivative going to be? If you think about it graphically, it's sort of becomes obvious, or it's easy to see. So let's say c is this number here. Then the graph of f at x equals c is just a horizontal line. It should be straight, going through c. So what does a tangent to this curve look like? Well, a tangent to a straight line is just the line itself. So what's the slope of this line? Clearly m is equal to 0, which should suggest, or should tell us exactly, that f prime at x is equal to 0, because f prime is equal to the slope. So it looks like if f at x is a constant, then f prime at x is 0. And another way to see that is to just use your limit definition, which is always a better way to, I don't know if a better way, but it's always a good way to come up with a rule or verify derivative. So limit is h goes to 0. Okay, so f at x plus h. Well, f at anything is c, so that would just be c minus f at x, which is again c, all over h. So that's just limit is h goes to 0 of 0 over h. Well, 0 over h is 0 over anything, as long as it's not 0, is 0. And we have a limit law which says that that's equal to 0. So it was true. So in general, d by dx of a constant is equal to 0. So that's what we call the constant rule, where c is a real number. Okay, so that's your constant rule. Okay, now we're going to put that rule together with 3 other rules. So these rules are not specifically for functions, but it's for derivatives of ways of combining functions. So let's say you have the derivative of f plus g. Well, the rule turns out to be that's equal to the derivative of f plus the derivative of g. And I'll prove that one in another video too. It's almost not necessary to prove, because it really just follows directly from some of your limit laws. So if you remember, one of our limit laws said the limit of a sum is equal to the sum of the limits. Well, basically it works for derivatives for the exact same reason, because a derivative is really just a limit. So the same works for differences. And then we also have a constant multiple rule. So if you multiply a function, then the derivative is just the derivative of the function times that constant. So this one we call the sum rule. This one we call the difference rule. And this one we call the constant multiple rule. So let's just see how these rules actually work. So let's say, as an example, you had f at x is, no, sorry, I'm going to write this in Leibniz notation. Let's say y equals x to the power of 5 minus x to the power of 2. Well, then dy by dx is just going to equal the derivative of the first one minus the derivative of the second one. So that's just the difference rule. So it says I can take the derivative of the first minus the derivative of the second. And then we can just apply the power rule, right? So 5x to the 4 minus 2x to the, and then if you want, to the 1, but you don't need to write to the power of 1 usually. Okay, so that's the derivative. So notice I just applied the power rule twice, and then since it's a subtraction, the derivative will be also. Or you could do, here we'll do one with the constant multiple rule. So let's say it was g at x equals 5x to the power of 6. So that's saying that g prime at x is just going to be 5, so the constant, times the derivative of this, times d by dx of x to the 6, which again now we can just, so 5 times, use our power rule, 6x to the 5, and then you can multiply the 5 and the 6. So 30x to the 5. Okay, so you should be able to see that we can now sort of apply these rules to any polynomial, right? So let's say you had, just do one example, f at x equals x to the 6 minus 3x to the 4 plus 2x squared plus 7x minus 1. So the derivative is just going to be the derivative of the first thing. So that's 6x5 minus 3 times the derivative of x to the 4 would be 3 times 4x cubed plus 2 times the derivative of x squared would be 2x plus 7 times the derivative of x, it's just 1, minus the derivative of 1, so constant rule, that's equal to 0. And now just multiply these numbers. So 6x to the 5 minus 12x cubed plus 4x plus 7. So hopefully you can see that, this rule will now apply to any polynomial, and that's greatly going to simplify our practice of taking derivatives.